Hey, how's it going, everybody? So, I just wanted to go over today's remote lesson. So, we're just going to be doing new content today and some practice around our energy concepts. So, we're going to be reviewing our energy practice problems. So, have those out. You're going to be doing quite a bit of work with those today. And then just kind of working through some new concepts. So, we'll go through those now. As far as homework goes, there's going to be the practice problems up to number 17. The Khan Academy exercise conservation of energy. You'll see that in the Khan Academy links. And you're going to go ahead and you can watch the videos if you want. You could skip them if you want. If you feel that you're pretty good just looking at the review sheet on there and getting the questions done, well, don't worry about the videos. They're like 15 minutes long. Also, we're going to have a quiz next class. And so study your notes, textbook, practice problems, and Khan work and get prepared for it. Okay, so let's start today by getting out your journal, your practice problems, your calculator, and your equations. Notice these supplemental notes. These might be a good place to study for the quiz coming up. And here's your links for Khan Academy. Okay, so today you're going to be using all those resources to get ready for your quiz coming up next class. You're going to open up your work energy practice problems. We're going to be doing quite a bit of work with these. So first of all, there was a problem number 12 on your practice problem set that was new. We have not gone over in class, and you were just to work it based on the stuff we had done previously. Here's the answers. Go ahead and check your work against that and see if you can confirm that those answers are correct. If not, work at it and figure it out. And you can always give me a message in Google Classroom if you're having problems. Okay. All right, let's go ahead and revisit number 7. So number 7 was asking about does the moon do work? Does the Earth do work on the moon as it goes through its orbit? And we said no due to the perpendicular relationship between force and distance. But now that we've looked at work and energy, we also can define work as changes of energy. And in this case, when the moon goes around the Earth, it's actually maintaining a constant radius, give or take a little bit, but as it maintains its constant radius, we would say that it's not changing height. Therefore, the gravitational potential energy, which is based on mgh, is not changing. And so in that sense, you would say that it is actually not gaining or losing energy. Therefore, it's not doing work that way. And the same thing can be said for kinetic energy. Actually, there is a constant speed as it goes around. And because of that constant speed, it's not gaining or losing kinetic energy. So from that perspective, you could also say that it's not doing work. Okay, so you could add those. Some people may notice, though, that there is actually an elliptical orbit between for the moon's orbit. And so there is actually some changes in energy that are kind of going back and forth, but netting out to zero in the end. So there's no network. But just to notice there's a little bit going on there, but we can kind of gloss over that for now. Okay, next question here was dealing with this thing called the work energy theorem, which just says that work equals change of energy. Now, I know for sure in the quiz that this question is going to be on there, so you want to get ready for this one. But what you do in a question like this is realize that because work is equal to this change of energy, in this case, change of kinetic energy, we would say that the work is actually the area under the curve right here. So you'd calculate your area and then set it equal to the change of energy. Now, in this case, the change of kinetic energy says that it started at 0. So it's really just looking at the final kinetic energy of 1/2 mv squared. So you just sort it out. And you say the integral of the graph is equal to 1/2 mv squared. And then you sort out the unit you're looking for, in this case, mass, by manipulating the rest. Okay. Should get 2.8 kilograms for that answer. This is a demonstration that we often do in class because of the way that this year works. I'm just going to do this one as a quick video for you to check it out. But go ahead and check out the video. It talks about conservation of energy of a bowling ball. Now, with this idea with a bowling ball, when we look at how a bowling ball drops through a pendulum motion like this, and it gains speed as it goes down, you can predict the speed at the bottom of the swing using conservation of energy. So what we have here is the potential energy is maximum at the top here, and then the potential energy becomes 0 down here, and the kinetic energy at the top is minimum or 0, and then when it gets to the bottom, it's at its maximum. Okay. Now, if we know what this potential energy is, related to this height displacement. We're only looking at the vertical displacement of height, by the way, so notice that. That's important. But then you can just set it up in the equation for mgh is equal to 1/2 mv squared. Notice that the mass is on both sides of the equation, so it cancels, and then you can come out with the velocity of the ball at the bottom. Check that out for number 13 on your practice problem set. Next concept that we're going to look at is using like a mechanical advantage idea that just shows you how you can take advantage of inclines in order to put out less force when you're doing work. Now, the idea here is, imagine if you're trying to get some heavy object into the back of the truck. If you try to lift it straight up, like this force times distance straight up right there, that's a lot of force to push up that small distance. And because human strength has maximum forces that you can put your body through, that becomes really, really hard. So to make it work, you can do something that takes advantage of mechanical advantage, where you put a ramp here, and by increasing the distance that you have to put that thing up there, you decrease the force. So even though you have to push it for a further distance, because of your muscles maxing out at a certain force, you can actually do it. And that's why we use ramps. Okay. Now there's an example like this. This is kind of using a ramp to get to the top of a mountain in a way. But this is just like looking at that idea. How much work does this bicyclist have to do to get to the top of the mountain? And to do it, he's actually got to push up not just the friction on this incline. Okay, so there is friction. It shows you like this average force. Now, because he's going up this long incline, he's like pushing through 75 newtons worth of friction for a total of 5 kilometers, right? So you just multiply those together to figure how much work he did along that incline. But that's not the only work that he did. He also did work against gravity, or increased his gravitational potential energy straight up the slope. And you can sort out how much total work he did through an equation like this right here. There is a part of this problem that has power in it. We're going to visit power next class. So just ignore 14C for now, and we'll just get back to that next class. All right, now the next question here is similar, but it gets a little harder. And so I'm going to go ahead and notice with this question, you're trying to get up this ramp here, and we do have friction involved. And so we're going to have to lean back into some of our lessons from earlier in the year. And if you go back into your journal and look back at inclined planes and friction on inclined planes, and then we were doing this whole like looking at net forces. Go ahead and look at all that, because I've got like a step-by-step to walk you through this process right here. But I think you can get to this right answer right here just by kind of carefully walking through the process and leaning into our old work. So just look at that one carefully, spend a little time with it. Now, once you're done with that, go ahead and do number 16 and 17. I'm not going to give you any pointers on these except the answers. But you guys want to go ahead and just see what are all these concepts of work that are leading up to those answers, and see if you can get to the right ones. Okay, now given those pieces of information, we're going to have a quiz next class. Get ready for it. This kind of shows you what to get ready for. And I just sort of put the formulas you want to be familiar with here, and a couple like pictures of problems that you might have, okay, like dealing with angles for work equals force times distance, using conservation of energy to say your potential energy up here will equal your kinetic. How can you use it to solve for the velocity when it hits the ground? You'll see one like that. Noticing something like this, if they both came down, how would their speeds compare? And then you've got one of these work kinetic energy theorem here, where you're going to look at the area under the curve being the work done, equaling the kinetic energy. You should be able to get that answer. So that'll be the review for the test. And then as any remote day goes, don't forget to do the attendance form. That's it, everybody. Have a great day. Enjoy yourselves.